In this video, we're going to talk about matrix multiplication. We're going to define matrix multiplication. We're also going to define the Hermitian matrices. So we're going to bring together the ideas that we had for scalar multiplication of vectors and adding matrices, as well as scalar multiplication of scalars and matrices. We're going to bring this together and we're going to call this matrix multiplication. So first, let's start out with the matrix vector product. Suppose A is an m by n matrix with the columns of A1 to AN, and U is the vector of size n. Then the matrix vector product of A with U is the first entry in the vector U multiplied by the first column of the matrix A. The second entry times the second column, the third entry multiplied by the third column, and etc. So let's take a look at how that would play out. So let's do by definition, let's do this matrix vector product. So it will be 2, which is this first entry, multiplied by the first column, which is 2, 1, 1. That comes from here. Then I'm going to have this -3, so -3, and it's going to be multiplied by the second column, which is 3, -2, and 5. And then it's going to be plus 0, that comes from here, multiplied by the third column, which is 3, -2. Do that consistently. So that would be it would be the third column is a -1, 7, and 3. And then plus 5, and then multiply by that last column, 0, 3, and 2. So let's go ahead and do the scalar multiplication. When I do the scalar multiplication, I'm going to get 4, 2, and 2. And I'm just going to use that as a plus and bring the negative in on the 3. So -9, 6, and -15. And then, of course, 0. Then my last one is going to be 0, 15, and 10. Now I'm going to go ahead and add these vectors like we expect. So I would start with 4 plus a -9 plus 0 plus 0 gives me a -5 in the first position. 2 plus 6, which is 8 plus 15 gives me 23. And then I have 2 minus 15 is -13 plus 10 is -3. So there is how we defined the matrix vector product. This allows us to take our linear system and write it as a solution for x in the vector equation. We can make x as being the variable, the x vector as being the variable. So basically that allows us to do this on this example. We can take the coefficient matrix, which is 2, 3, -1, 1, 2, 1, 1, 3, and 3. Then our vector matrix will be all the variables, x1, x2, and x3. And this, of course, will equal the constants 0, 3, and 7. So our vector matrix multiplication does have applications. Suppose you are trying to determine the best city in America and you're looking at Los Angeles, Chicago, and New York. You decide that the average temperature in July is important, and so you give it a positive, 2.3, positive being good, negatives being bad, quote bad. Colleges within a 30-mile radius of the city you're looking at it's really important to you, so you give it a 0.6 weight. Superfunds are not as detrimental to you as it could be, so it is a -0.05 weight. And then, of course, the crime is really important to you, or the amount of crime is really important to you, and it's detrimental, so you gave it a weight of -0.2. So let's make the matrix T as being the entries of the temperature, collies, and superfund and crime. So 77, 28, 93, 254, 84, 38, 85, 363, 84, 99, 1, and 193. Now, if you take a look at it and you think, oh, well, crime's not too bad in New York, well, let's actually see where it lands in terms of the matrix vector multiplication. So I'm going to call my weights the W vector, of course, which makes sense. So 0.23, 0.46, negative 0.05, and negative 0.2. So let's do T multiplied by W. And we're going to get the 0.23 multiplied by that first column, which is 77, 84, and 84. And then it's going to be plus 0.46 multiplied by the next column, which is 28, 38, and 99. And then minus 0.05 multiplied by that column, the third column, 93, 85, and 1. And then lastly, I'm going to multiply the negative 0.2 times the final column, which is 254, 363, and 193. Now, when we multiply all these together and add up the columns, or add up the entries on these vectors, I get negative 24.86. I get negative 40.05, and I get 26.21. So in terms of ranking, New York actually ranks the best. It ranks at a positive 26.21, where the next one behind that is actually Los Angeles. And then behind that, of course, would be Chicago being the lowest in terms of numbers. So here's a real-life application of a matrix vector multiplication. So let's take a look at some theorems. Now this section is full of theorems, and the reason it's full of theorems is because we've got to define the way matrices are going to interact with each other in terms of multiplication and what it looks like. So our first theorem that we're going to get is the equal matrices and matrix vector products. Suppose A multiplied vector A multiplied by vector, or excuse me, matrix A multiplied by vector X will be the same if for B being matrix B and X being the vector for every X entry from the complex numbers, only if the two matrices were equal to begin with. So that brings us to matrix multiplication. Now suppose that A is an n by n matrix and B1 to BP are the columns of matrix B. Then the matrix product of A and B is m by n matrix, where the column I is a matrix vector product AB. Symbolically, what I have is I have A and then multiplied by each one of these individual vectors of the column. What it looks like this, using this definition for matrix multiplication, which is probably different than what you're familiar with, would look like this. So I'm going to use A in blue, so A multiplied by B, which will be in red. This is going to be equal to my A matrix, which is 1, 3, 1, 0, 1, 0, 1, 1, 2, multiplied by the columns, the first column in my B matrix, which is 2, 0, and negative 1. And then, I'm just going to partition that off. Then I'm going to have my matrix again, 1, 3, 1, 0, 1, 0, 1, 1, 2. This is my A matrix. And then the column of my the second column in my B matrix, which is negative 5, 1, and 2. I'll partition that off. And then my A matrix again, so 1, 3, 1, 0, 1, 0, 1, 1, 2, multiplied by that last column in my B matrix, which is negative 1, 0, 1. Okay, now I'm going to use the definition of a matrix vector multiplication so I can break this apart even further. So I will have 2 multiplied by 1, 0, 1, and then I will have plus 0 multiplied by the 3, 1, 1, and then I will have plus a negative 1 multiplied by the 1, 0, 2. Now notice what I'm doing here is I am taking each entry in the column to 0, 1 from the first column of B, and I'm multiplying those entries like I did before with my matrix vector multiplication, and I put that into the multiplication of each one of these columns. Again, I'm going to partition this off, and then my next one here, this is of course the matrix, my next one here is going to be similar, so it's going to be -5 multiplied by the first column again, 1, 0, 1, and then plus 1 multiplied by the second column, which is 3, 1, 1, and then it's going to be plus 2 multiplied by that last column, which is 1, 0, 2, and that, I'm going to partition that off. And then my last one here is going to be the -1 multiplied by the 1, 0, 1, and then plus 0 multiplied by that middle column, 3, 1, 1, and then lastly plus 1, and then my last column again, which is 1, 0, 2. All right, now let's clean this up. So starting in this first grouping here, I'm going to get the matrix, I'm going to get the multiplication of 2 times 1 plus 0 minus 1. So I have 2 minus 1, which is 2. I'm going to have 2 times 0, which is 0, plus 0, which is 0, plus 0. So that's going to be 0 right here. Then I'm going to have 2 times 1 plus 0 minus 2 gives me 0. That is my first column in my matrix multiplication. Now I'm going to do my next one. -5 times 1 plus 3, so I'm at -2, plus 2 is 0. -5 multiplied by 0 is 0, plus 1 times 2 is 2 times 0, which is just going to give me a positive 1. -5 multiplied by 1 plus 1 gives me -4, plus 4 gives me 0. And then my last one here, 0. And then my last one is going to be -1 multiplied by 1, which is -1, and then 0 times 3, which is 0, plus 1, so that gives me 0 in that first position. So that's 0. And then my next one would be -1 times 0, and then plus 0, so that's 0. So that gives me 0. And then I'm going to do my last entry, which is going to be -1 times 1 plus 0, and then plus 2, so I end up with a positive 1. Now, this is actually kind of a cool multiplication here. The reason I say it's a kind of a cool multiplication is if I just take row 1 and divide it by 2, I end up with the identity matrix. And that's going to mean something in our next section. So I'm going to leave that there for right now, but that's kind of a cool multiplication we ended up with here. Now let's take a look at my next theorem here. My next theorem is, suppose A is an n by n matrix and B is an n by p matrix, then for every I less than m and every j less than p, then I can do this individual entries of A, B are given by the AI1, the B1j, and this is what we normally see when we see multiplication of matrices outside of linear algebra. Now let's redo matrix multiplication using this method. When I use this theorem instead of how I defined it before, I'm going to offset it so I have -3, 1, 2, -1, and I'm going to offset my B matrix up here, and that's 0, -2, 4, and 5. And the reason I'm offsetting it is by this theorem, I'm going to multiply this entry by that 0, this entry by that -2, and add that together. So it reminds me that I'm going to be multiplying these together to get this number right there. So when I do that, I'm going to get -3 multiplied by 0, and then plus 1 multiplied by -2, so the entry is -2. So let me just fill that in right there. So that entry is -2. And then I'm going to do this and this to get that entry. So it's going to be -3 multiplied by 4 plus 5 multiplied by 1. So I get -12 plus 5, which gives me -7. So -7 is going to go into this entry right here. And then I'm going to multiply this by this to go into that entry. So 2 multiplied by 0, and then plus -2 multiplied by -1. So that gives me a +2. And then my last entry here is going to be, I think I've used all my colors now. This one and this one is going to go right there. So 4 multiplied by 2 plus 5 multiplied by -1. So I get 8 plus -5, so that gives me 3. So my resulting vector of A multiplied by B is the -2, -7, 2, and 3. So this is doing it entry by entry by the definition, or by the theorem up above. So let's take a look at our next group of theorems. And we're going to have a bunch of theorems here, so just bear with me. And what we're going to be doing now is we're going to start collecting these theorems so that we can understand how matrices are going to interact with each other. So our first theorem that we get is the zero matrix theorem, which says if I take any matrix and I multiply it by a matrix of the appropriate size of a zero matrix, so all the entries are 0, I get the zero matrix. Similarly, it doesn't matter if 0 is on one side or the other, as long as it's the appropriate side, then it will work out. And what I mean by appropriate size is if we come back up to this example, notice that these entries, so these number of columns have to be the same as these number of rows. So if I have a matrix that is an M by N, then I can only multiply it by B if I have an N by some other number, say P, like we did above. Notice how these have to match. The number of columns in the A matrix have to match the number of rows in the B matrix. So that's what I mean by the appropriate size. And then, and also by the theorem up above, we end up with the new matrix, we'll call it C if you will, right at C, which is going to be an M by P. So it will have possibly a different size if the two matrices you're multiplying are not square. All right. So then we end up with the next bit of theorem. Again, a lot of theorems in this section, so we know how matrices are going to interact with each other. Matrix multiplication of the identity matrix. So we have the A matrix multiplied by the identity matrix of the appropriate size. And it doesn't matter which side you multiply it on, as long as it's the appropriate side. It basically is like saying in the real numbers we're multiplying by 1. Just like up here, this is saying in the real numbers, it's similar to saying in the real numbers that we're multiplying by 0. But matrices are different beasts, so don't just say, oh, it's true 3 times 4 is 12 and 4 times 3 is 12. That is not true of matrices. We do not have that that property that we get with real numbers. So be aware of that. The next one is the distributive property. So this still holds true in real numbers and matrices, is that A multiplied by B plus C is the same thing as A multiplied by B plus A multiplied by C. Similarly, if I have B plus C times D, then it's BD plus CD. And order matters. Order matters. Terribly, terribly important. Order matters. In fact, you know what? Let's take a look at this. Let's multiply this the other way. So we know what the answer is when I have AB. So let me just erase this. I'm going to bird walk for a moment. And let's do the multiplication where we have B is the lower matrix down here, so 0, -2, 4, and 5. And let's do the A matrix up here, which is -3, 1, 2, and -1. Same kind of thing. Again, we're going to multiply these and these, so we get 0 multiplied by -3 plus 4 multiplied by 2, and so I get 8 in the first position. And you can see that it already, we know that these aren't the same, but let's go ahead and continue through. So these and these, so I have 0 multiplied by 1 plus 4 multiplied by -1, it gives me a -4. And then I'm going to multiply these, and so I have -2, -3, plus 2 multiplied by 5, so I get 16. And lastly, these and these, which is -2 multiplied by 1 plus 5 multiplied by -1, and I get -7. So the B multiplied by A order does matter. You noticed here when I did this, I got a different matrix than when I multiplied the A by B. So we have to be careful. Order matters with matrix multiplication. Let's keep moving down. So, of course, we are always talking about being in complex. It's a larger number set. Suppose A is an n by n matrix and B is a p by n by p matrix and alpha is the scalar. Then the order in which I multiply the scalar doesn't matter. So I can multiply the scalar after I've done the matrix multiplication. I can do the scalar and one of the matrices and then multiply it by B. Or I can do the scalar multiply by B and then multiply that answer by A. We have associative. We do not have commutative. I'm going to be really clear. We do not have commutative. That's the one up above. We do not have commutative, but we have associative. So I can do BD first and then multiply that answer by A, or I can do AB first and multiply that answer by D. Then we're going to talk about the matrix multiplication and inner product. So we consider the vectors U and V, which are the entries are from the complex, and we have n entries. As an m by 1 matrix, if we think of it this as an m by 1 matrix, then my inner product is going to be U, the complex conjugate transposed, the dot product multiplied by V, and we note the complex conjugate transpose as the adjoint. So that, as we remember from a couple of sections back, that is the reference to the adjoint, which is basically the conjugate transposed. That brings us up to the next theorem, which says, suppose A is an n by n and B is an n by p, then the conjugate of that multiplication can be found by doing the conjugate of each one individually and then multiply them, or multiply them and then find the conjugate of the entries. Remember, this is really for the complex, and we start out with the complex before we bring it into the smaller real number set. Matrix multiplication and transpose, so I can multiply them first, then transpose them. Be very careful on this, extremely careful. If I decide that I want to transpose them first, then I transpose B first, then I transpose A, and then I do that multiplication. This is AB transpose, where this is B transpose multiplied by A transpose. So that is kind of important here. So now let's kind of just bring all of this together. So here is some matrix multiplication, and they want us to find AB transpose. They want us to do B times the identity. It's going to be the easiest. They want us to find C multiplied by A multiplied by B, and they want us to find B raised to the third power. So what we can do is we can transpose first, or we can multiply. Now, these are the same matrices from up above. So these were the matrices that we did up above, and we already have answers for the A multiplied by B. From before, A multiplied by B was -2, -7, 2, and 3. So we know that A multiplied by B transpose is going to be equal to, and I already forgot that. How terrible is that? It was -2, -7, 2, and 3. -2, -7, 2, and 3. So -2, -7, 2, and 3. Now I'm going to transpose this, and so that's going to give me the -2 and 3 stay positions, but -7 moves and 2 moves. Remember, rows become columns, columns become rows with matrix multiplication. We know from our theorem that B multiplied by and this is a identity of size 2, so it's 2 rows, 2 columns, is just going to give me B, so there's no stress there. And then I'm going to make sure that when I do the AB times C that my sizes match. So C has 3 rows and 2 columns, and we know what AB is. It is a 2 by 2. Because these two match, we actually can do that multiplication. What we couldn't do is we couldn't do AB multiplied by C, and that's because AB is a 2 by 2 and C is a 3 by 2, 3 rows, 2 columns, and these don't match, so I wouldn't have been able to do that multiplication. We've already done the AB again, so that's the easy part. So the CAB, because we know we can do it like this, is going to be equal to, and again I'm going to put my C down here, -5, excuse me, it will be, let me do that in black. Here we go. So I'm going to bring this one down here, and 5, -1, 3, 0, 4, 3, and then my AB, so -2, 2, -7, and 3. Same kind of thing, these and these, so that's going to be 5 multiplied by -2 plus 0 multiplied by -7. That entry is going to be -10. And these, so 5 multiplied by 2 plus 3 multiplied by 0, so that is going to be a +10. And these, so -1, -2, plus 4 multiplied by -7, so -28. -28 plus 2 is -26. I'm going to do this and this, so -1 and 2 plus 4 and 3. That gives me -2, 12, so 10. I'm running out of colors here. I guess I'm going to have to go back to my green again. These and these. And that's going to give me 3 multiplied by -2 plus 3 multiplied by -7. So I ended up with -6 plus -21, which gives me -27. And then my last entry is this and this. So 3 multiplied by 2 plus 3 multiplied by 3. So I end up with 6 plus 9 is 15. So this multiplication, bring it all over here so it's a little cleaner. So -10 and 10 and -26 and 10 and -27 and 15. So there is CAB. All right. Let's give you a couple of more, a couple more theorems. So suppose A is an n by n matrix and B is an n by p matrix. I know you're going to get sick of this. That AB, which is the adjoint, and remember adjoint is the complex conjugate and its transpose. So AB, I can multiply AB together and then do the complex conjugate of it and then transpose it, or I can find the adjoint of B, multiply it by the adjoint of A, because remember the asterisk means adjoint. So I give you a lot of theorems, and you almost feel like, wow, I got hit by a bus. Let's talk about where we are at this point. What these theorems do, and the results from our matrix operations previous section, gives us the rules on how matrices will interact with various operations, and we have defined it in terms of addition, scalar multiplication, matrix multiplication, conjugation, transpose, and adjoints. We're going to use these and we're going to use them often, but there are some things that you want to think about. One of the things you want to think about is, unless you have a rule for it with a matrix, don't do it. It's probably not going to be defined, so don't do it. We call these operations that we've done with these theorems, we call these the algebra of matrices. Now, another thing to think about is that every column vector, we've never called them this, but they really are an n by one matrix, where n is the number of rows. And so the number of entries in matrix. So we've not column that, but really every column vector is an n by 1 matrix. So all the theorems that we have learned in this section are going to apply to column vectors. And then we're going to take this information and it's going to be able to help us define multiplication so it's not so unnatural. Now let's take a look at our last bit of information, which is the Hermitian matrices. So let me just move this up so we can talk about these. So we have this first theorem that says, suppose A is an n by n matrix and X is a column vector. In other words, it is an n by n matrix whose entries are from the complex plane, and we have n number of entries. The same thing with Y. Then I can do the A multiplied by X inner product with Y, or I can do X inner product of the adjoint of A and then Y. Theorem is in your book for your viewing pleasure. The other thing we get is the definition of what a Hermitian matrix is. A square matrix is Hermitian or self-adjoining if the original matrix is equal to its complex conjugate transposed. So, the adjoint. Our next theorem is the Hermitian matrices and inner products. So, before we move on though, let's talk a little bit about how we define these in terms of real numbers. So if we're talking about Hermitian matrices in real numbers, these are the set of symmetric matrices. So Hermitian matrices in real numbers are the set of symmetric matrices. Just want to throw that out there in case you were wondering what the heck. Last theorem, before we do a couple of examples, it says suppose A is a square matrix of size n, then A is Hermitian if and only if this holds true for all x and y in the complex plane. Let's do some Hermitian inner products here. So we're going to use it by our definition. So the first thing we're going to do is we're going to find each entry and we're going to find the complex conjugate of each entry. So we're going to conjugate our first vector, which is 2, negative I, 3, positive 2I, 4 plus 5I. Now we're going to go ahead and multiply that. They do the inner product of u. So again, here's my u. So I am going to do each entry, I'm going to do u1 multiplied by, you should be u and v. What? That should be v. Okay. So we're going to do the u1 multiplied by the v1. So what I'm doing is I am doing the 2 minus I multiplied by the 7 plus 2I. Then I'm going to do the u2 conjugate multiplied by the v2. So this is going to be 3 plus 2I multiplied by the 5 plus I. And then my next one is going to be the complex conjugate of u3 multiplied by the entry in v3. And this is going to give me 4, and that should be a minus. It should be a minus. Don't minus some t. Okay, there we go. Minus, that should be a minus there. So 4 minus 5I, and then I'm going to be multiplying that by 1 plus 6I. And then this is what I'm going to get for each one of these. So this is going to be equal to, so my first one is 16 minus 3I. My second one is 13 plus 3I. And then my last one is 34 plus 19I. Now, the Hermitian inner product is going to be the sum of all of my real numbers plus the sum of all my complex numbers. So I'm going to take 16, I'm going to add 13, I'm going to add 34, and I get 63. I have a negative 3I plus 3I plus 19, and I get plus 19I. And there is my Hermitian inner product of those two complex vectors. Now let's see what it looks like in real numbers. Well, you're going to be like, what? So, of course, and this should be a V, that for this is strictly just the dot product, the inner product, because the complex conjugate of a real number is just itself. And so this is just going to be 2 multiplied by -7 plus -5 multiplied by 4 plus 4 multiplied by -3, -14 minus 20 minus 12. My final answer, of course, is a scalar, and it is a real number. And I end up with, let me see. So I have -14, and then minus the 20, and then minus the 12, and I end up with -46. So that's it for this video.